So now we'll be starting with the tutorial of the controllability week. So the controllability week, as discussed during the theoretical lectures, it is finally divided into two parts, part 1, part 2, which would be covered over a period of 2 weeks, that is week 3 and week 4. And today we'll carry out the tutorial for the part 1, and second part would deal with the tutorial in controllability part 2, covering the rest of the lecture slides. So this is the outline for the tutorial problems. So the problems which we would see today would consist of the controllability tests from the lecture slides 21 and 20 and 43. We would also have the control input design, the reachability for the discrete time and the time varying systems. One practical example is considered in problem number 6, which is the hot air balloon. Then the rest we do with the controllability check under different conditions, and also the rank equivalence condition. So this problem 1 deals with, given the matrices A and B in the linear time invariant system, which obviously was obtained by linearizing some nonlinear equations of motions of an orbiting satellite around some steady state solution. So 4 states have been identified, x1 to x4, with their physical significance in the nonlinear equations. We have two inputs, u, which is divided into u1 and u2, where u1 is the radial thrust and u2 is the tangential thrust. So the first part of the problem is we want to test whether the system is controllable or not. Second part is quite interesting in the sense that we want to ensure the controllability of the system under one of the inputs. Say for example, if u1, which is the radial thrust, if the radial thrust, if we have lost complete control over the radial thrust, so can we say that the system is still controllable by using only the control signal u2, and vice versa. So this problem was taken from the book Encyclis, the problem 3.2. So this book was also put into the one of the references books. So if you want to go through other problems, you can take a look at it. So let's see. So from slide number 43, from the lecture slide, we know that this LTI system is controllable if the controllability matrix is of full rank, right? So this is a pretty much standard test because we are already provided with the A and B matrices. So we can compute the, first of all, the controllability matrix and then its rank. So since the dimension of the A matrix is 4 cross 4, this would be your controllability matrix, and if we compute the rank of this matrix, you would see that it is equal to 4, which is equal to the dimension of the state space system. You can also use the MATLAB command by using this, which is the rank of the controllability matrix of A and B. So CTRB is the function, is the inbuilt function in MATLAB, which you can use to compute the controllability matrix given the matrices A and B. So since we have identified if we are using both the controls, the system is completely controllable. Now we want to test if the first input fails, meaning to say if u1 is completely equal to 0, then if you pay attention to the B matrix, so this B vector is corresponding to u1 and this one is corresponding to u2. So if u1 fails, then we would have the, or we can label this as b1 and b2. So our B matrix is basically two column vectors b1 and b2. Okay, now if u1 fails, then we don't have access to b1, but we have access to b2. Similarly, if u2 fails, then we have the access to b1 instead of b2. Okay. So once u1 is equal to 0, so in that controllability matrix, we would be using only b2 vector instead of using the complete B matrix. So similarly, we compute the controllability matrix and then we compute the rank. And you can also compute by yourself that the rank of this matrix is equal to 4, meaning to say that even if u1 fails, that you still you still have the power to control the system by using only the u2 signal. Now, if the other input fails, so we compute the controllability matrix and we see that the rank is less than 4, meaning to say if u2 fails, then you cannot completely control the system by using only the input u1. Okay. The second problem is the follow-up problem 3.2 of the same book, where we are again provided with the LTI system A and B matrices. So given the initial conditions at t is equal to 0, a, b, we want to derive an input that will drive the state to the origin in t seconds. Okay, the follow-up part of this. So the first part only computes the parameterized solution in terms of a and b. The second part, this a and b is taken as 5 and minus 5, and we do a further analysis by uh, computing that how the input and state trajectory would behave if we specify three different values of capital T, that is 1, 2 and 5, and how do the trajectory appear after. So this is pretty much important part, the last part, because by solving this problem we would also come to one conclusion which we have also discussed during the lecture slides, that controllability is not in fact equal to to ensure that the system would be stable, because we here the idea is we want to find a control input that can take a non-zero initial condition to zero initial condition, but it would stay there for the rest of the time. It is not mandatory. So by looking at the lecture slides from 17 to 21, you can compute the control input by using this formula. So in fact, we have explicitly computed this formula to compute the control signal in terms of the Gramian matrix. Now here one important thing to notice is that this input is basically an open loop input. Open loop input in the sense, say let's say we have a plant which interacts with the input output signal as u and y, and one internal state variable is x. Okay, now this input which has been designed here, it is taking some, let's say we call it the controller, which is generating this u signal. Now u signal we call it open loop because this control or this controller, which is another subsystem, is not taking any information either from y or from x. Okay, so we can compute the control input using this formula, which requires to compute the Gramian matrix, whose formula is given here. So once all the computation is done, we put the initial conditions as a and b and the final condition at time t as 0, 0. So after putting all these equations and the parameter values, you would find this complicated u where this delta is given by this. So this is just a simplification of solving this integration involved in the Gramian matrix. But once we go to the part B, which involves further putting the values of t and the initial conditions that are a and b. So, so the first part is, so we have directly plotted the figures, because once you have the complete formula for the u, you can also compute an analytical expression. Now once we have the analytical expression and we put it into we give it to the plant, we also compute the trajectories x1 and x2 to show that whether they are reaching to the origin in the finite amount of time. So here the first case is we have taken when t is equal to 1 and the initial conditions are 5 and minus 5. Okay, so computing that control input and applying to the plant, we see that In 1 second, the state trajectory have reached to the origin. Okay, because we have already computed the system is completely controllable. Now, if we see at t is equal to 2, this is the input signal which you are seeing in the dark blue, and again starting from the initial conditions, we reach to the origin in 2 time seconds. So one thing here is interesting to note, that once we have largened the time from t is equal to 1 to t is equal to 2, one straight thing is to notice that the control signal, the energy required in the control signal is quite less than what it has been there in t is equal to 1. We will also do some computation or to quantify the amount of energy used in the control signal. Similarly, if we compute for t is equal to 5, again starting from minus 5 and 5, we reach to the origin in 5 time seconds, where the control signal is now given by this. So since the system was controllable, these trajectories only shows that how the control and the state trajectories behave whenever we want to see that the initial conditions are reaching to the origin in certain amount of time. But the interesting point here to see that what would happen if we want to simulate the same system beyond t is equal to 1. So up to t is equal to 1, we had seen that it has reached to 0. But if we keep applying the same input, what we had computed, you would see that the system basically reaches to infinity. It is not necessary that it will stay at 0. Now, if the state trajectories are staying at 0 until, t tends to infinity, then it means that the system is a stable system. So this trajectory is for t is equal to 2. Now, if we see beyond 2, again we notice that the system is exploding towards to infinity. Similarly, these trajectories are at t is equal to 5, and after 5 reaching to 0, they can take any path. Although the system was unstable, that's why for the same control input what we had computed, the trajectories are reaching towards to infinity. So you can also compute the energies of the input signal. This you can also visualize by the amount of efforts the actuator has to put into to steer the trajectories from non-zero initial condition to zero initial condition. So if the time we have taken is less, meaning to say that the control input has to be act quite fast in comparison to if we want the system to be a bit slower, right? Because we here we need that in t is equal to 5 seconds, the system can reach from non-zero initial condition to zero initial conditions, right? Which means that it would take more time and the control actions would be slow. This is also the reason that the energy for t is equal to 5 is way less than what energy is required at t is equal to 1. Okay. The problem 3 is again the subsequent problem of the same book, where now we are considering a discrete time system with A, B, C matrices given by this. So the first part of the problem is we want to know whether x1, which is given by this, is reachable. If you recall the definition of the reachability, that from the zero initial condition we want to reach to some non-zero initial condition, and here we have specified that conditions. So starting from the origin, we want to determine that whether there exists any control input such that we can reach to this x1 at t1. So if yes, what is the minimum number of steps required to transfer the state from the zero state to x1? Since this is a discrete time system, we can compute the number of steps also, and what inputs do you need, right? And the second part is determine all the states that are reachable. Third is a separate problem which we will come on to later. So first we'll discuss the part A and part B of this problem. So if you recall from the lecture slides number 28 to 29, you can directly use the controllability test as a rank test to determine whether the system is controllable or not. But at the same time, you need to recall that for the continuous time system, the concept of reachability and controllability coincides, but for the discrete time system, it may coincides or it may not. So first of all, we compute the controllability matrix, which is given by this one, by using the standard formula which we had seen in the problem 1. And computing the rank of this controllability matrix, we find that it is a rank deficient matrix because it is not of rank 3. Now, if we want to test whether this state at t is equal to t1 is reachable, meaning to say that this x1 should belong to the image of this controllability matrix, and to say this, that there should be some eta vector such that this equation is satisfied. So if we are able to find, if we put this x1 which is given here, we have the controllability matrix with us. Now if we are able to find that eta vector, then this state is reachable. Now one straight way to compute this eta would be possible if we compute directly this one, but we cannot take the inverse of the controllability matrix because it is a rank deficient matrix. It is non-singular, sorry, it is singular matrix. So by computing ad hocly this or searching for this eta, we find that for this specific eta, which is minus 130, we see that this equation is satisfied, meaning to say x is c eta, where eta is now given by this, meaning to say that this x1 belongs to the image of the controllability matrix. Okay, so this state is reachable. Now since the rank of 2, we could also say that x1 would also again belong to BAB, because this part is B, this is AB, and this is A square B. Now if the rank is 2, we can only take this part, the rank of this sub matrix, let's say, would also be 2. So for doing the computation of that, how many number of steps are required and what are the values of those steps of the control signal, we would parameterize the solution of the discrete time system. Since it's a discrete time system, we can write it as in algebraic equations. So starting from k is equal to 0, we write x1 is equal to ax0 plus bu0, where x1 is now given by this. Similarly, x2 would be ax1, where x1 has been computed over here, plus bu1. So we can again parameterize x2 in terms of u0 and u1. Now if we see this step, the first element is 0, but we need the first element to be 3. So only in one step we cannot reach to that state value. But if you pay attention here, selecting u0 as 3 and u1 as minus 1, you would see that u0 plus u1 would be 2, and similarly this would be 2. So only in 2 steps we can reach to the value which is specified initially, 322. And the values of the control signal would be 3 and minus 1. Okay. So going back to part 3, here another discrete time system has been chosen with different AB matrices and also the dimension of the system. We want to comment on the reachability and controllability subspaces. Now at the same time we also need to comment upon that whether both the concepts are equal for this state space system or not. Okay, so before that I think we have skipped this part, which is determine all states that are reachable. So here it is written B, and so it should be B. So you can compute the basis for the reachability subspace, which is given by the range space of this controllability matrix. And this basis you can select so that these two vectors are linearly independent vectors. Now there could be any two linearly independent vectors which you can choose as a basis, and then writing x for those AB, you could find all the combinations of x. Now choosing this as a basis, which are basically the first one is the 0 1 1 element, and another we have chosen such that it becomes linearly independent with the first vector. So substituting this here, we see that all those x's which are having this arrangement BAA will be reachable. Now also there, all the elementary operations you could perform over these elements would also be reachable, because they will form another basis of the same space of the controllable range space of the controllability matrix. Yeah, so this is the C part. So if you compute the controllability matrix for the matrices given here by this A and B, we want to comment on the reachability and the controllability subspaces, which you can do by computing the rank of the controllability matrix. So this has been done here. Now it is clearly visible that the rank of this matrix is 1, meaning to say that the system is not controllable. But at the same time you would notice that the matrix A is a singular matrix. And if you recall from the lecture slide, we have said that the reachable space is basically a subset of the controllable subspace. So it means you can find some input which can still transfer the state from x0 given from A and B to the origin. Right? And the system is controllable to the origin, but it is not reachable. Okay. The problem 4 discusses the reachability for a discrete time system. Again, we have taken the AB matrices and the C matrix with 0 initial condition, the discrete time. So here the problem is to find that whether there exists a sequence of inputs that transfers the output from origin to some non-zero value in finite time. If the answer is yes, determine such a sequence. Second part deals with the characterization of all outputs that can be reached from the zero output in one step. So here one important difference you will notice, that so far we have talked about the controllability and reachability of the state vector. Now here we talk about the output vector. So the first question arises here, that whether the formula what we had studied of the rank condition is also applicable to determine the, or let's say the reachability of output. That we can compute the controllability matrix, and then determining the rank would ensure that this system is output reachable, and similarly the characterization is possible. So the answer would be no, first of all, because we have computed the AB matrices for this state space system, where the state vector is x and AB matrices are being a part of this algebraic equation in this way. So we need to parameterize this state space or this state equation in terms of the output equation to finally use the rank test. This you can do by using, so if you recall the output expression, we have yk is equal to c into x of k. Now if I advance this k at time to k plus 1 at time, both sides, we would have yk plus 1 equals c xk plus 1. Now since this is the state equation, I can use this equation here to finally substitute at ax plus bu. Okay. Now from here, if my C is a non-singular matrix, I can write xk as C inverse yk and cbuk would stay as it is. So this part would be my A bar and this part would be my B bar. And now I can replace my y by y, which is an output variable, by let's say some x bar. So this would become x bar k plus 1 A bar x of k plus B bar u of k. Now this equation become almost similar to the state equation what we have been seeing from the beginning. So using these matrices A bar and B bar, I can compute the rank of the controllability matrix, which would be given by CB. If I substitute this B bar and A bar is this part CSE inverse and B bar is CB. So the controllability matrix, to test whether my output is reachable or not, this matrix would become CB and CAB. So I need to check the rank. And computing the rank, we noted that it is a full rank matrix, meaning to say that the system is reachable and the required input exists. Now in a similar way, what we had done for the previous problem, you can compute that how many number of steps are required and what are the control signals which can take the origin to some non-zero state at some time t1. So the required input we have computed as u0 is equal to -1 and u1 is equal to 2 would take you to the desired state. Right. So if you recall the second part, it says the characterization of all outputs that can be reached from the zero output in one step. So this origin for y0 would be 0, implies that x0 would also be 0. Therefore, if we want to reach in one time steps, I would write y1 is equal to c of x1 and c and x1 is given by bu0, because if you see this equation, I just substitute directly k is equal to 0. Now k is equal to 0, we have x0 is equal to 0 and u0 would come as it is, because u0 would become a parameter. So simplifying the CB matrix, we would have 1, 2 and some parameter u0. Now for any u0, this is the y which we can reach from the origin in one time step. So if we choose u0 is equal to 1, then y1 would become 1 and 2 respectively. Okay. Problem 5 deals with the reachability of a time varying system. So given an LTV system with A matrix, which is a constant matrix, but B matrix is a time varying matrix because of the inclusion of the exponential term. So the first part that we need to show that it is controllable at any time t0. So the BCD part we'll discuss one by one. So first we check the controllability. Now for the controllability, if you recall one of the key result that we need to first we need to compute the Gramian, and if that Gramian is having a full rank for all t0 and t1, meaning to say the system is completely state controllable. The controllability grammar can be computed by using this formula, where this phi is the state transition matrix. Now, since we have this A matrix, which is pretty much simple, you can directly compute the state transition matrix without any difficulty. And by putting that matrix and multiplying with this B matrix, we finally obtain this controllability grammar. Now, for any T1 and T0, you can check the rank of this matrix. You would find the rank is always 2, meaning to say that the system is completely controllable. The part B of this problem is that suppose we are interested only in x2. So we discard the first equation and we consider that x2 dot is equal to x2 plus e to the power minus t into ut. So the problem is that is it possible to determine ut so that the state x2 is transferred from x to 0 to the 0 state at some time t is equal to t1, where x2 of t1 is 0 and then stay there, right? So if you recall the previous problem, when we computed the control input, we have ensured that during that time the states would reach towards to 0, but it was not possible to guarantee that the states will stay at 0. But here we need to design a control input and ensure that once it reaches to the origin, the state, it would stay at 0 afterwards. Okay. So if the answer is yes, find such a u of t. So let's see. So we need to find an input that will satisfy x2 is equal to 0 for all t greater than equal to t1, because x2 at t1 should reach to 0. Now if you see the solution of only this state equation, we can express the solution in this way, where the state transition matrix would be an exponential term because of the non-dependence of the A matrix on time t. Now putting t is equal to t1 in this equation and equating this part equal to 0, because we need to ensure that x2 at t1 should be equal to 0. So for that we require that the right hand side should also be equal to 0, and once it reaches to 0, if we are not supplying any input to the plant after that time t1, we could ensure that it would always stay at 0. Okay, so let's see. So first of all, we define some input which is given by e to the power 2t into at plus b for all time between t0 and t1. With this input, first of all, we need to show that it reaches to that x2 at t1 is equal to 0 at time t1, and afterwards x2 should be equal to 0. Okay. So this required two equations to be solved. So the first one we have obtained from here. We just need to substitute ut into this expression which we have specified here, and since this computation is between t0 to t1, we would use this ut. Now the second part, that ut should be equal to 0 for t greater than equal to t1, which would happen if a t1 plus b is also equal to 0. Now we have two unknowns and two equations. Solving, and these are the linear equations, so solving these two equations, we obtain a as this and b is this. Substituting this a and b into this u, we finally obtain this control input, which ensures that the state of the system would reach to 0 and would stay there afterwards. This you can also visualize in these simulations, that we have specified t0 as equal to 1 and x0, which is x at t0 is equal to 5, and we have chosen our time window t1 is equal to 2. Okay, so we need to ensure that starting from t0 the state should reach to 0 by time t1, and afterwards it should stay at 0. Okay, so supplying the same control input what we had computed, you would notice that the desired objectives have been achieved. Now the third part of the problem is that in part B, let T naught is equal to 0 and study the effects of the sizes of T1 and X naught on the magnitude of UT. So here you should recall one thing, that in one of the previous problems we had computed the control energy. So we had noticed that if the time is longer, then the control energy is less. So the same behavior we are expecting it here. Why? Because now there is more time in which we need to ensure that the system reaches to the origin. So the control actions could be slower instead of being faster. So let's see. So for T naught is equal to 0, we already have the control input which we have computed. And if I compute the energy from 0 to T1, because afterwards it is 0. After T1 it would be 0. And seeing and computing this finite integral, we computed this formula in terms of T1 and x2 naught. So we notice that the energy of UT increases as xt naught increases. If we keep the T1 constant, then as xt naught increases, the energy would increase. Now keeping xt naught as constant, as T1 decreases, the energy would increase. Almost the similar kind of behavior what we had seen in one of the previous problems. Part D, that for the system in B, that is considering only the second state equation, determine if possible a u of t so that the state is transferred from xt naught to x21 and then stay there. So now this is a more generic formula which we are looking for, because in part B we need to ensure that x2 at t1 should reach to the origin, but in the part D x2 of t1 could be anything, right? It could be 0 also. So whatever the results we are going to obtain in part D would also be applicable to part B directly. So again, it requires the computation of the control input, where we need to ensure that x2 at t1 should be 0. In fact, here it should not be 0, but x2 of t1 should be some value, let's say x21, and this x21 could be 0. And since we want the x2 to stay at x21 after t greater than equal to t1, meaning to say that the derivative of that equation should be equal to 0, so that it becomes a constant value starting from that initial condition at t is equal to t1. Because if I see this equation would have its initial condition at t is equal to t1, and at t is equal to t1 we have already ensured that it has reached to x21. So if I put the derivative of this equation equal to 0, meaning to say that this trajectory would stay at x21 only. So from here I specify ut as same as before, that e to the power 2t at plus b between t0 to t1, because we have already seen that this ut applying within this time would take me to that x21. Okay, and if I put this equal to 0, I would obtain u of t as minus e to the power minus t x21. Okay, again simplifying these expressions, so finally we obtain this a and b, that if I put this a and b here, this control signal, which is again an open loop control signal, there is no feedback path, which would be the topic of the week 5, that this open loop control signal has given us the desired objective, that the state trajectory has reached to x21 at time t1 and it stays there afterwards. Okay. The problem 6 is a hot air balloon where the approximate equations of motions are given. This problem is taken from the book on linear systems by Caleb, which is an example 2.3. So these equations are the linearized equations around some operating conditions. So theta, U, H and W have some physical significance. The theta is the change in the temperature of the air balloon. U is the change in heat which is being added here so that this balloon can fly. W is some vertical wind velocity. So here the point which you pay attention that we have taken only the vertical wind velocity because the wind has 3 components, but here we are considering only the vertical component and this is acting as disturbance. Okay, and H is the change in altitude from the equilibrium altitude. So first of all we need to determine two transfer functions from both the inputs where U is the in fact a control signal and W is a disturbance. So we need to compute U by excuse me H by U of S, one transfer function, another transfer function is H by W. And the second part of the problem is that we need to ensure we need to determine the controllability from both the individual inputs U and W. Right. So all that those three differential equations we can express them in terms of the state space representation where the state variables would become theta, V and H. This is the A matrices and the B matrix with respect to two inputs U and W. Now wind, if we go by the physical significance of these two control inputs, we know at the outset that by using U, you can control the system. But also, it would be interesting that whether we can control by W also. Right? Because W is basically a disturbance, which is the wind velocity. So if you are lucky, then the wind can take you to the desired height. Right? So if we compute the eigenvalues of the system, this eigenvalues are given at minus 1 by tau 1, minus 1 by tau 2, and there is one eigenvalue which is located at the origin. So the transfer function either you can compute by using the standard formula which we had seen many times, that is C into Si minus A inverse into B. So by putting this B as this one time and another this, you would obtain two different transfer functions with respect to U and W. So using this formula for the present system with A, first we can see the computation of the Si minus A inverse. So you can compute that matrix which is given by here. Now since here we have two different inputs, so the first test which you can do once we have the AB matrices, knowing these AB matrices, I can compute the controllability matrix and then compute the rank of that matrix. So this would be a straight test, but here try to visualize the controllability of the system without performing any tests first of all. So first we'll compute the transfer functions in the sense that let's say we would have H of S. If we are considering as two inputs, it would be a vector of U of S and W of S. Let's call it H1 of S and this is h2 of s. So we need to compute these two transfer functions. So applying the superposition principle, we can compute h1 by putting w is equal to 0 and compute h2 by putting u equal to 0, and then compute two different transfer functions. When putting it into the vector, it would give me the complete representation of the system in terms of the transfer functions. Okay, so the similar way we have done here, that computing h by u by putting w is equal to 0. So since three equations were involved, we have computed h by v. See here. So from here I can compute h by v, which would be basically an integrator. From here I can compute theta by u, the transfer function, again by considering the initial conditions equal to 0. And from here I can compute basically v by theta and v by w individually. Okay. Now putting all this expression h by v, v by theta and theta by u, we obtain this transfer function. Now putting u is equal to 0 and computing h by w, so we need to substitute h by v and v by w, which is this transfer function. So here one thing to note here, that all the eigenvalues of this matrix Si minus A inverse, which is an important matrix because this is nothing but your state transition matrix. If I take the inverse of this matrix, it would give me the state transition matrix, and we know that almost all the characteristics are embedded into the state transition matrix. So if I compute the poles of this matrix, we have the poles at 0, minus 1 by tau 1 and minus 1 by tau 2. Now if all the eigenvalues are visible in the transfer functions, meaning to say that that I can control that system represented by that transfer function. Okay, so if I see the transfer function h by u, I see all the eigenvalues are present here. Now if I see the transfer function other one h by w, we see that one of the eigenvalues 1 by tau 1 or tau 1 s plus 1 is not available, meaning to say that it has been cancelled out by some part in the numerator. So if I see the input output signals, that is h and w, that mode or that eigenvalue is basically hidden from the input output signals. So you can also visualize that how that eigenvalue has been cancelled out. Say for example, let's write this equations. So the first equation is let's write this here, theta 1 dot theta 1 plus u. Another one we have h dot is equal to v, and w. I think we have written correctly. So 1 by minus 1 by tau 2 v sigma theta plus 1 by tau 2. So this should be 1 plus tau 2. Okay. So now from here we need to compute the transfer function h by w of s by putting u is equal to 0. Okay. So if I see this equation, so this one is pretty much standard. If you take the Laplace transform both sides, it is nothing but an integrator. So we would have h by v of s is 1 by s. Now if I substitute, when I substitute u is equal to 0 in this equation, I would have theta dot is equal to minus 1 by tau 1 theta, and taking the Laplace transform, I would get s plus 1 by tau 1 theta equals 0 because u is taken as equal to 0. Now coming back to the third equation and taking the Laplace transform, I would have s plus 1 by tau 2 be equal sigma theta plus 1 by tau 2 w. So all these variables are the function of s. So either we can use the hats symbol, which we have been using in all the demonstrations. So now we notice that s plus 1 by tau 1 into theta is equal to 0. So there could be two outcomes from here. So now if this tau 1 is positive, if this tau 1 is positive, then I can say that theta would definitely be equal to 0. But if I do not substitute, or if I do not assume anything on the positivity or negativity of this tau 1, then because if tau 1 is on the, or if this eigenvalue is on the right hand side, then it is no longer possible that theta would approach towards to 0. But if the eigenvalue or the root of this part is on the left hand side, then theta would definitely be equal to 0. So without making any assumptions and knowing this fact, so we multiply the whole equation by s plus 1 by tau 1. Okay, so here I would have s plus 1 by tau 1 sigma. The sigma is a scalar, so s plus 1 by tau 1 into theta would become equal to 0, and here I would have s plus 1 over tau 1 tau 2 tau. Okay, now computing the transfer function from here, or v by w, as we would have s plus 1 by tau 1, and in the denominator again we would have 1 by tau 1 and s plus 1 by tau 2. Okay, as a function of s. Now this v by w, once multiplied by this h by v, I would have h by w as h by v into v by w, all in the s domain. So you would notice in this part we would have 1 by s, right? So the eigenvalue 1 by tau 1, which was hidden somewhere, is now explicitly visible to us, which is being cancelled out. So because this numerator and denominator part, would cancel out each other. So if I see only the signal h and w, I won't be able to see this mode from the signals. Okay, so now it is pretty much clear that the system is controllable from u, but it is not controllable from w. Okay, but at the same time we should notice that if s plus 1 by tau 1 polynomial is having the roots onto the left hand side, then this theta would always be 0, even if it is not controllable. Then we have another concept which is weaker condition than controllability. Okay, the problem 7 is that, is it true that the rank of this matrix equals the rank of this matrix, and if not, under what condition will it be true? So this problem is taken from the book by C.T. Chain and problem 6.3. So if you pay a close attention to this matrix, you would notice that it is nothing but a controllability matrix. Now if I multiply by A matrix, the whole controllability matrix, I would obtain this. So in one of the in one of the results, we have noticed that I can express, so this row we have used as the rank. So row means that I am interested in computing the rank of this matrix. So the rank of this matrix I can express as the rank of A and the rank of the rest of the matrix. Now if the rank of the rest of the matrix, or in fact this is the matrix of which I am interested in computing the equivalence with the previous matrix. So I can express this matrix as the multiplication of these two one. Now if A is a non-singular matrix, if A is a non-singular matrix, then I can express the rank of only this matrix, which is nothing but the matrix, the controllability matrix. Okay. So under the condition that A is non-singular, I could say that the equivalence holds. Otherwise, if A is a singular matrix, then the equivalence will not hold. So you can do a quick example or quick check also. Say let's suppose A, which is not relevant, which is not related to here, that A is some m cross n matrix, and there are other two matrices, let's say C and D, which are the square matrices of dimension n and m, and both these C and D matrices are non-singular matrix. So then we would have the rank of the matrix AC would be equal to the rank of A, and it would be equal to the rank of the matrix D and A, D into A. So to do a quick check, say suppose M we are taking M is equal to 2 and N is equal to, let's say, 5. Now this, the dimension of this AC matrix would be your M cross N, because A is M cross N and C is N cross N. Your DA matrix would be dimension of M cross N also. Yes, it would be having the same dimension as this AC, and row A is M cross N. Now since M is a lesser number than N, so the rank of A would be equal to 2. And the rank of DA again would be equal to 2, and similarly the rank of AC would also be equal to 2. So this equality would always hold, which is equivalent to saying that pre-multiplying and post-multiplying a matrix by a non-singular matrix would not be able to change the existing rank of that matrix. Okay. So problem A deals with the controllability check. So this is an important problem. In fact, this is also one of the important results, which is speaks about specifying the controllability condition in terms of computing the Jordan form of the matrix. So far, if we speak about the controllability checks of an LTI system, we had studied the rank test, the PBH test, and some by characterizing their spaces also, by computing their grammar. Now this test is in terms of the Jordan form. Let's say for a given A matrix, if we compute its Jordan form, Jordan canonical form, then by seeing only the distribution of the B matrix, we can directly comment on the controllability of that state space system. Okay, so pay attention here. So this has been already specified in the model form. So it has one real eigenvalues, which is lambda 1, and two pairs of complex conjugate eigenvalues. So this has been expressed as in terms of the model form, because if because eigenvalues occur in the complex conjugate pairs, so the eigenvalues are alpha plus minus j beta. So j beta 1, and similarly for 2. Okay, so all 5 eigenvalues are distinct. So here we need to show that the state equation is controllable if and only if B1, B11 and B21 are non-zero, or B1, B12 and B22 are non-zero. Okay, so directly by checking the condition of the B matrix, we can comment on the controllability of an LTI system once the A matrix is given into the model form. Okay, so we'll see the proof of this, but this is also one good result. So we know that the controllability is invariant under any equivalence transformation. So we can introduce a non-singular matrix transformed into Jordan form. So this matrix we have been using P, computing this P inverse, we get this. So computing this A bar, we see we have this PAP inverse which we have been seeing from the beginning. So now this matrix becomes a complex matrix. And from the beginning we know, or we knew, that there are 5 distinct eigenvalues, where 2 eigenvalues are the complex conjugate pairs and the 5th one is the real eigenvalue. So I can express all these 5 distinct eigenvalues in the form of a diagonal in the A matrix. But if I do not want to express my A matrix as a complex matrix, I can transform into a real matrix by using that model form which was already given into the question. So the A matrix does not contain any complex terms. So similarly, applying the transformation on the B matrix, we would obtain B bar. Now recall from the lecture slide number 43 that the LTI system is controllable if and only if the controllability matrix has full rank. So now on this A bar and B bar, we can apply the controllability test, that is the rank test, and from there only we would obtain the conditions on this B, the elements of the B matrix. So you would notice the state equation is controllable if and only if B1 is not equal to 0 and these two part are also not equal to 0, which is again equivalent to saying that B1 is not equal to 0 or either of the combination of the B part associated with the eigenvalues are also not equal to 0. Okay. So this is another good test to do a check on the controllability, that if it is possible to compute the model form, then by looking only at the B matrix, we can comment directly on the controllability, or you compute the rank of the controllability matrix. So this is the last problem, which again is of the controllability check, that for time invariant systems, we want to determine that the pair AB is controllable if and only if minus AB is controllable. Meaning to say that if I take a negative A matrix, then that new pair I could also say is controllable or not. Okay. Now we also need to show that is this true for time varying system, meaning to say that AT-BT pair or the controllability of AT-BT pair is equivalent to the controllability of minus AT-BT, whether this hold or not. So we need to show in the time invariant case, and we also need to show for the time varying case. Okay. So let's see. So for time invariant system, we know that the pair AB is controllable if and only if the rank of the controllability matrix is equal to n. Now assuming that A is an n cross n matrix, minus A comma B pair is controllable if and only if I form a controllability matrix of that pair, which is given by B minus AB. Here we have A square, so it becomes positive, and similarly in this way. Now again I can express this whole part as this part, where I have extracted the negative terms in terms of another matrix which is composed of the identity matrix of appropriate dimensions and the rest this is. Now this is row is basically to compute the rank. Now if you recall the previous result, this matrix is a non-singular matrix, and this matrix is what we already know that it is controllable, so the rank of this matrix is already equal to n. And since it being the pre-multiplication and post-multiplication by a non-singular matrix does not change the rank, so the rank of this matrix would definitely be equal to the rank of the original AB pair, the controllability matrix formed by the original AB pair. Okay? So by changing the sign of the A matrix does not change or does not affect its controllability properties in the LTI case. Okay. Now, seeing for the LTV case, for some particular example, let's select A of t and B of t as these matrices. For this A matrix, we can compute the state transition matrix, which is pretty much easy to compute, and then computing the controllability Gramian and checking the rank for every T1 T0, we found that this pair A of t and B of t specifically given by these combination, it is not controllable at any time t. So now we will check the controllability of the pair with a negative A sign, which is given by this. So this will become positive, the rest of the element would stay as it is 0. So for this new pair, we have the state transition matrix given by this, and the controllability Gramian is given by this. So now you would notice that for any T0, we can find a T1 so that WC, the controllability Gramian, is non-singular, and this pair is controllable at any T, although the original pair AB was not. So that equivalence holds for the LTI case, but that same equivalence does not hold if we are talking in the time varying case. Okay.